All right, guys, page 191. Oh, number 61. Is that what you're saying? All right. You can have a teacher that can actually write. Okay. Alright. 61 talks about a different way to do some of the work. And somebody came by my office and was asking me about it, and I used to teach both ways directly, and then I noticed students were getting confused doing half of one and half of another. But I still want to assign it just to show you there is a different way to do. So the example they give, let me see, what do they give here? Yeah, so if you want to take 328, for example, and convert it to base 5, we normally start with, how do we normally do this? Let's do it the normal way, and then we'll see. It's thinking I'm not like fully OCD, or else it'll become crazy. Yeah, what do we do first? Yeah, so 1s, 5s, 25s, 125s. That's too much. Cool, so you always go like too much, or make sure that you actually went far enough. And then we divide 125 into 328 and go from there, right? Let's go ahead and get the answer here, and then we'll try it this other way that the problem describes. All right, let it go, Jeff. How many times does 125 go to 328? Twice. Good. So 328 minus 250. 78. So I got 78 left to take care of. 25 goes into 78 3 times. Yeah, there, 25. So now I got 3. So do I need any 5s? I just need 3 here. Now here's the interesting part. Let's attack this from the other direction. Take 328 and divide it by 5. So this is the other method that the book describes. So instead of seeing how much the largest can take care of and seeing what's left over for the next place to take care of, this actually kind of does that the other way around, which is a little bit weird. 5 goes into 328. Yeah, 6 times 30, 20, 65 times, and that would be 325. So that's remainder 3. Now take 65. 5 goes into 65. I always know 5 goes into 60 12 times, right? So 65 is 1 more 5, so it's 13 exactly. So remainder 0. So now I've got 13 left here, right? So 5 goes into 13 twice, remainder 3. And 5 goes into 2 no times, remainder 2. Now read these backwards. 2303. 2303. Right? Not like David Blaine level, but still, it's sorry. No, David Blaine, is he still out there? Look him up on YouTube. There's funny parodies of David. But that's the process that they ask you to do. So it's. I'm not going to get into the full math reason why this works, but I just want you to know there's other ways to do some of what we do. If this makes no sense to you at all, don't let it confuse you. I want you to have a way that you do these. If you love this method, you can do them all like this. That's awesome. I don't mind. But it's just really neat to see this work, and you can. Maybe some of you guys will start to think about, why does that work? I don't want to feed you everything. See if anybody's at all curious about it. So can you go from there? Is that so? Anything that we've done, you could do it this way. You want to do another one like that, or you want to move to something else? Yes.
Number 12.
Oh, okay. So we'll move to something else. So are we cool with this one? This is number 61 in section 4.3. This is the process they talk about. So they just want you to apply that same process to something. Couple things. Okay. And it doesn't only work with base 5, it works with any base. the same process. 12?
Yeah.
In this section?
Yeah.
Okay. So, what did I say about if I'm coming from somebody else's system to my own system? So if I'm trying to go from, and that's anything, going from Babylonian to mine, going from Mayan to mine, going from base 12 to mine. Not Mayan, but mine. What is it about that? Versus starting from Hindu-Arabic or starting from our place value system, going to somebody else's. Which one's easier? Does anybody remember? Let's try this. How do you do this? Do we know how to do this? What base is this in? It's in base 12. When it's given to me in base 12, I know what the places are and I know what each place is. That's the easy way. That's the easier way to do it, right? If it starts in somebody else's, I know what all the places are. If it starts in mine, I write the other places. I don't know what the hell it is. It's all blank. That's when I have to divide, subtract. It's a little bit weird, right? And then I even got weirder ways to do it. But this is in base 12. That kicks ass. So I got 1, 0, 0, 5. I've got 4 places. What are all the places? What's this place? 1s, 12s, 144s,
1728.
1728. So how many 1728s do you have? 1. Plus none of these, plus 5 of these. You put that back together, that becomes base 10. Kick ass. So when it's already in somebody else's base, I know what all the places are. When it's in my base, I don't know what these are. They're all blank, which is always worse. Is that cool?
So what's the answer?
So let's see. How many 1728s do I have?
1.
1. So I got 1 1728 plus none of these, plus none of these, plus 5 of these. So it's 1728 plus 5, 1733. So that represents 1733 base 10. So if we had 12 fingers, we would represent the idea of 1,733. We would represent that with these numerals here. Right? I'm desperately hoping some of you guys, even if you don't understand what this really captures, you can do the math pretty simply, but I'm really hoping some of you guys really understand that that number means 1,005 just because we have a base 10 number system. If we had a base 12 number system, these numerals together would mean something else entirely. But we would just know it. We would have been brought up in it. We would count on our fingers until, I guess we'd have 12 toes too, maybe, just for symmetry. Go up to 24 just based off your fingers and toes, right? Alright, cool. Maybe the weirdos, the people with only 5, oh, you're weird. Alright, you're strange. Slaves still living. That would be the reverse of Princess Bride. You have 6 fingers. No Princess Bride things. Sort of, I don't want you to know. Alright, anything else from homework? So homework is going really well? Otherwise? Chapter 4 stuff? Alright. Because a little bit later I'm going to pass the project stuff out. It's got a little timeline on it. It's for you creative types to really unleash, right? Like I said, I've had people in the past give me stuff that improves on our number system. I'm not saying you have to do that. I'm saying that, who knows, you might stumble into something. I've had people turn in the bare minimum, which is fine. That's enough. So you can get as deep into this as you want to. If there's no other questions, though, I'm actually going to get into chapter 8. If there's no other questions. Oh, before I get too far, quiz on chapter 4 will happen Monday. Apparently, everybody understands chapter 4, so we're going to be ready for it. Cool. You're good, man. I got your... Okay. I saw your picture. I'm like, don't send me pictures when you hurt yourself.
Should I stay? Because I can't really write, so...
You can absorb.
Okay.
Yeah.
All right.
You can ask somebody else, maybe later you can take copies of the notes. Okay. So there's no other questions. We're getting into chapter 8. That's our next, or not 8, sorry, chapter 5. So in chapter 5, there's some stuff that looks familiar. This is one reason why I like chapter 5. We already did chapter 1 where we looked at patterns, and that could be anywhere from numbers to those weird faces with the sticks coming out of the side of their head. Do you remember that problem? Or the some of you guys do. So there was problems like chapter 5. Let's just remember these. So we're going to get a little bit deeper into these kind of things today. We're going to get a little more mathematical with this. So what would the next 2 terms be in that sequence? Yeah, it looks like add 3, so add 3, add 3. And there might be another one, like on the last test, there were 2 different ways to look at one of the sequences I gave, so I was accepting both answers. So I make a problem up. It's really funny, you guys are not used to this, but I can make a problem up, have one idea in mind for the answer, and then there's a whole other answer that works. But this is one place. Sequences, it could totally happen. So what I want to do, what would suck if I asked you find the 98th term in this sequence? Do you feel like doing that? I wouldn't either if I thought I had to do what we just did over and over and over. But doesn't it make sense that since we just keep adding 3, shouldn't there be a quicker mathematical way to get there? Alright, makes sense. Now be careful, a lot of people just tell me it's 3 times n or something, where n is the one. Well, that's automatically no good. The first one is 1, not 3. So that doesn't quite work. So let's analyze this a little bit, and then we're going to generalize to the formula that always works. First thing I want to tell you is, this is called an arithmetic sequence. The fact that it starts with the letter A is nice, because this sequence is based on addition. We're going to talk about sequences that are based on multiplication, and for some reason those are called geometric. So unfortunately I called something that starts with the letter N. But this is an arithmetic sequence. And let's just overanalyze this bad boy. So if A1 is 1, and it is, how do I get from 1 to the next thing? How do I get from 1 to 4? What do I do? Say it? Add 3. I love it. So arithmetic sequences are kind of nice. You think about them as how to move from place to place. So if I start at position 1, and every step I take is 3 feet big, now I'm at position 4. I take another step. So how do I get to A3, which is 7? From 1, I take how many steps to get to 7? No, I go 6, but each step is how big? Each step I take is how big? 3. Are you guys with me? Every step I take is 3. So how many steps did I have to take here? I took 1 step of 3. How many steps am I going to have to take here? 2 steps, of course. And here, what can I do? 1 plus 3 times how many steps to get to where I start? I'm there, right? No steps. So this is part of what math is all about. And sequences can be very simple, but they can be very complex. So we desperately want to develop some math so that we can work with the ones that are really weird. Or this is not even a difficult sequence. This is not a difficult sequence at all. Just keep adding 3. But if I wanted to get the 98 term real quick, I'd much rather have an equation that I can just plug 98 into. All right, equation, what the hell is the 98th term? Tell me. Right? So can anybody extend this? What would A and B? This gets a little weird. Notice how the first term, I took 0 steps. The second term, I took 1 step. The third term, I took 2 steps. So how many steps do I take to get to the nth term? N minus 1. I love it. If I start at 1, I always take 1 less step than where I want to be, because I started at the first place. Sometimes, if you're studying sequences, they can actually let you start A0, which would actually be really nice. But I won't do that because the book starts at 1. So I want to keep it consistent. So this would be 1 plus 3 times, like you told me, n minus 1. I want to take this many steps from 1 to get to this term. Stop there for a second. I love this class because you guys have such different backgrounds in math. Some of you guys look at me like, yes, go on, I get this, and some of you are like, what's going on? Can I clean this up a little bit? So again, an is 1 plus 3. What would I do algebraically to that to clean it up a little bit? Who to what? Distribute. So we get an equals 3n minus 2. Yes. So let's check it. How do I check to see if that's right? I have the 5th term here, right? Staring me in the face. So if I do this, a5 better come out to be 13 or else I've screwed up somewhere. So what happens when you plug a 5 in? 3 times 5 minus 2 is 13. Think I was looking like, oh, please. You never know. All right, now on this one level of this is I hope you realize this is not very complicated math. I think most of you guys kind of realize that. But just the idea, this is pure math in action. Look for a pattern. Formalize the pattern, so then I'm able to answer this kind of question easy. What's the 98th term then? Yeah, because it would be 3 times 98 minus 2. 3 times 98 is 294 minus 2. 292. It's crazy. All right, I like it. So at the heart of it, we knew there must be a quicker way to get an answer like what's the 98th term. Instead of just writing all the freaking terms out till we go crazy. All right, that would be somebody sitting in the corner of a rubber room, just keep on writing the terms out. It's not good. Yeah?
Where are we?
I wish I knew. Oh, this is section 5.7.
Page 270.
Yeah. So we do kind of like pick and choose out, or I did anyway. I'm not just say we. But I picked topics from the book that weren't just going to be repeats of stuff you've probably done before. I don't know if anybody in here has ever done arithmetic and geometric sequences. Has anybody ever done that before? Yeah? What class was it?
Oh, okay. Something in high school.
Something in high school. Okay, good. In high schools, you never know. I saw high schools giving grades for lunch before. So high schools do. I guess you know this kid is going to fail. Which one? No. This is a true story. We saw lunch grades and somebody got a C, and we were concerned if they needed somebody to sit with them when they ate. But I'll let that go. Yeah, so high schools have all kinds of weird little classes they do, but normally in college there's not going to be too many places to see this kind of thing. All right, so let's formalize this even further. This distance between each, this is 3 here, this is 3 here, this repeated distance is called the common difference, which makes sense. It's a difference between two things. It's common. It just is the same always. So remarkably enough, in a formula, we call this D. D in this case is 3, so in general, it's the distance between terms. Cool. So you can identify very quickly if it's arithmetic. If I don't just keep adding the same thing, it's not arithmetic. It's not based on addition. 1 is important, and that's A1. It's remarkable. So now look at what we got. So AN we got for this one was, let's start back up here. Let's go to the general one. Was this, right? So what was 1? More generally. Why did I put a 1 there? Because that's where I started. So that's A1. That's the first term. And hopefully I didn't want to just straight up define A2, A3. I'm hoping through this you guys have picked up A7 means the 7th term. AN means you tell me what N is, and I'll tell you what that term is. That's why it's based on N. So keep going. So in general, for any arithmetic, any arithmetic sequences. If I can identify A1, what was 3? D. And then n minus 1 because I take one less step to get to that term. So if I have an arithmetic sequence staring me in the face, I know it's arithmetic because I already noticed it keeps adding the same damn thing. And I can just look at the first term and I've got an expression for any term I want. So if I wanted the 18 millionth term, thank God I don't have to write 18 million of them out to see what it is. So let me give you one to try.
So this is true for any arithmetic
Any arithmetic sequence must follow this rule, period. And it makes sense because an arithmetic sequence will continue to add the same thing. So if I start here and I go this many steps, let me do that again. If I start here and I go this many steps, I'll end up where I want to be. Is that cool? Anybody ever taken statistics at all? A few of you guys? That sounds very much like a z-score, for example. Take so many standard deviation steps away from the mean. No? Too long ago? Okay. I'll let that go. So here, try this one out. So find AN. Find A17. The common difference, yeah, how far apart they are.
And AN is
The nth term. So you have an expression for A.
okay.
Yeah. You can always identify this. And then if it's arithmetic, you can identify this. So if it was 2, 9, 18, it ain't arithmetic, it's something else. Sounds like I say arithmetic. So what is D here? 7. That's crazy. What is A1? 2. That's amazing. So then AN is A1 plus D times N minus 1. Start here and go this many steps. I think the book puts the D at the end, but we're just used to seeing it in the front, so I'm going to keep it there. So AN equals 2 plus 7 times N minus 1. And if you want to, you don't have to, but you can clean this up a bit. It'd be 2 minus 7 plus 7n, so it'll be 7n minus 5. Doesn't matter. As long as you have somewhere to plug n, you can figure out what A whatever it is. So you can do it either form, either this or that. I don't care. Hopefully most of you guys are like, no, I got to simplify that. Good. It's a good way to feel. So A17 would be 7 times 17 minus 5. 114. Cool. All right, maybe. So, I mean, this is a very, and of course you should have been exposed to this already. I don't know if you picked up on this. It's a very rudimentary showing of the power of mathematics. And of course, math goes beyond just pattern observation. It really does. But at the heart of it, it's find the pattern, write a generalization of that pattern, use that generalization for other things. I mean, that's a big chunk of it. Now, here's something a little more interesting. So hopefully you guys agree with me. That's interesting, but not really interesting. And you guys are like, interesting is pushing it by itself, Jeff, but it's all right. Here's what's really interesting. I don't think I've told the story. Maybe I've told the story, but I don't care. There's an urban legend in math. And it wouldn't make a very exciting movie if you collected all the urban legends of math. But, oh well. That says there's this guy in math called Gauss, and Gauss did way too much. It was just not fair. He should have left some stuff for other people to do, but I don't think he had much of a life. I don't know. He did so freaking much. So supposedly, when Gauss was really young, he was in grammar school. The kids were going crazy. The teacher's like, oh my God, this is going to drive me crazy. The teacher said, all right, kids, take the numbers 1 through 100, add them up, and then let me know what it is. And then he sat down, he started reading the paper or whatever. He's like, this is going to take him a while, because, 1 plus 2 is 3. 3 plus 3 is 6. And keep going. And I haven't even made it very far yet. Holy shit. But Gauss, a little smart ass, he figured out a way to do it like in 10 seconds. And he brought the paper up to the teacher. Teacher's like, what? So the teacher sat down and did it himself. And the students are all watching, And he's on 1 plus 2 is 3. 3 plus 3 is 8. You got the right answer. What the hell? And the answer is kind of cool. So, obviously I put the dots there. But this is every number from 1 through 100. And he wanted to add them all up. I don't know if anybody already knows this. A little shortcut. When you add, you can add whatever order you want to. So Gauss said 1 plus 100 is 101. 2 plus 99 is 101. 3 plus 98 is 101. So then he just had to figure out how many pairs are there. Well, how many pairs are there? 50, because there's 100 numbers. Divided by 2 is how many pairs there are. And he did 1 plus 100, because that sum will keep repeating, because then you just step in, step in, step in, step in. So you get 50 times 101, which is 50/50, which is neat. It's just neat that the first 100 natural numbers add up to be 50/50. It just feels good. Right? Or maybe it's just me. I don't know. Maybe it's just math people. I've never not been a math person, so I don't know what it feels like as a non-math person. But it's just neat. Okay, maybe. So we actually, does it make sense what we just did? It makes total sense, right? And it doesn't have to be separated by 1. It's any arithmetic sequence will work this way. The sum of a sequence that's arithmetic, if I have a finite number of them, I can do it this way. So for example, let's do another one. So if I have, what you got, Jeff? I don't know, Jeff. 4, 9, 14, up through 34. Sure. Let's do this so we can check it. Let's do this so we can check it. Let's not go crazy. So what do I mean by that? Let's just go up to this far here. You can do it, Jeff. So is that arithmetic? Yes, thank God. I added correctly. Good job, Jeff. What is D, for example? 5. And A1 is 4. And what's 1, 2, 3, 4, 5, 6? So I got 6 things here, right? And what do I say? A6, the last term is 29. So I'm kind of overanalyzing everything I know, because I'm going to make a general formula for it after we do this example. So the first step is this step. And this step was to figure out, what was that step to do? The step figured out, what did it do here? Why did we do this? What is this? Why did we do this? Pairs, to see how many pairs there were. Because then pairing them up and making a common sum, right? So I just want to know how many pairs will there be. So how many total numbers are there? 6 divided by 2 will tell me how many pairs there are going to be. And what's the repeated sum? Yeah, see, just to check it, 4 and 29 is? 9 and 24 is? 33. So it's 33, right? Is that cool? So the repeated sum is the first one plus the last one. That's going to be the repeated sum. So I get 3 times 33 is 99. And do it real quick. What's 4 plus 9? 13 plus 14 is 27. Plus 19 is 30. 46. 70, 99. Yay! So if you actually add them all up, you get 99. So I prefer this way. Right. And it's just because there's a pattern to the numbers. So there should be a quicker way to do math with them because there's an inherent pattern in there. So that's what this formula is taking advantage of. So what's the general formula? Thankfully, I'm going to use the letter S for the sum. So in general, Sn. So this would be the sum of the first n numbers. So this was because doesn't the sequence keep going? But I just wanted the sum of the first 6. That's all I wanted. Right? So the sum of the first n. What was this? N. It was how many I wanted, right? So this will be n. Cut in half to see how many pairs. And don't worry if there's an odd number, you're fine. You actually just end up cutting the middle number in half. It still works. Times, what was this? A1. And what was this? A6, which actually more generally, AN. Because if I have a 3,000 long list, it's going to be A3000. That's going to be the last, whatever the last term is. So there's a second equation. And by the way, just so you know, on the next test, I will let you, we'll actually together on the review day, we'll create a formula sheet that you'll be allowed to have. I'm not going to make you memorize these, even though most of them are very easy to remember. I'm going to be really nice. Why not? All right, I just want to see what it feels like. Well, don't let my other classes know. All right, so how do you feel about that? Is that cool? All right, so let's get to the weirder stuff. The weirder stuff is when you multiply. Why was this equation so nice? Because I'm adding a bunch of stuff that are based on addition. So that's going to go beautifully together. I'm adding a bunch of additions. Oh, that's no problem. That's why this formula is so nice. When I have a sequence based on multiplication, and I want to get a formula for adding so many of them, it's not going to be as nice, because addition and multiplication don't play together as well as addition with addition does. I don't know if you guys are with me. You'll have to show me, Jeff. All right. So now let's talk about what's known as geometric sequences. These are the ones based on multiplication. So for example, I have this here, 2, 6, 18, 54. This sits very much like a problem that was on the first test for some of you guys. Obviously this is not arithmetic, because here I added 4, here I added 12. Well, screw that. It's not arithmetic. I know right away. So how do I check to see if it's geometric? Yeah, you take 1 divided by the one before it. So 18 divided by 6 is 3. 54 divided by 18 is 3, thank God. 6 divided by 2 is 3. Right? So what do you think? D was the common difference, because how do I check to see if it's arithmetic? Is I take 1, subtract the one before it. Take the next one, subtract the one before it. So we use the letter D for the difference. What am I creating here? Well, let's not use a D again. And I like quotient, but we don't use Q because I can't make the letter Q too well. Plus, it's just not the one we use. These are all ratios, right? So we're going to use R for common ratio. So here, R is 3. What's A1? That's crazy. So let's develop the general formula for a geometric sequence. So figure out what whatever term is you want. So what would so A2 is 6. How did they get there from 2? Multiplied by how many 3's? 1 3, right? So to get to A3, I started at 2 and I multiplied by how many 3's? I multiply by 3, and then I multiply by 3, and I'm at A3, am I not? Yep, so I take 2 and I multiply by 2 3's. A4, I'm going to start at 2, I'm going to multiply by 3, crazy. So can we go to AN? I'm going to start at 2. I'm going to multiply by how many 3's? N minus 1. So it's that N minus 1 thing again. I don't know if some of you guys realize the N minus 1 could have been N if only we would have started at A0, but the book said let's not do it, so we're like, oh, screw it. That's why it's not as clean as it could have been. And then just to make sure you guys understand, how many 3's did I multiply this by? To get to 2, what do I multiply 2 by? How many 3's? None of them. Which is a really good way of remembering that 3 to the 0 power is 1. Because if you don't multiply by any 3's, you stay the same. 1 does that. That's why 3 to the 0 is 1. Maybe. So now we can take this and generalize it. So this is what we got for the specific sequence. So in general, let's write it what would it be in general. What was the 2? Where'd that come from? What was that for this? A1. So you start at A1. What was the 3?
Ratio.
Yeah, the common ratio, what I keep multiplying by. And then, of course, N minus 1, bam. So there is our third equation today. Really, that's enough equations. No math class, I'm going to stop. But the idea behind it is very, very simple. I mean, creating that equation was relatively easy. So here, you guys try this one. Find K21 for this sequence. What you got, Jeff? I don't know. Obviously, geometric sequences are going to grow quicker than arithmetic would. And then you have like sequences called exponential growth sequences, which sounds like a horror movie. Either a monster, the blob is growing exponentially, or the virus is covering exponentially more. You know, today it's here, tomorrow it's there. Zombies every damn where. Or whatever the virus does. Obviously, I watch 2 people. Walking Dead. Fear the Walking Dead. I hear the Walking Dead on Sunday. What the hell's the next show going to be? Whatever it is, I'm going to watch it. Come out. Let's see. Yes. So A1 is 5. R is 3. So then AN is going to be 5 times 3 to the N minus 1. Now, just to make sure that this doesn't happen. Yes, sir.
What is the N stand?
Which term you want. So if I plug in here 2, let's just check this.
Okay, yeah.
If I plug a 2 in there, 2 minus 1 is 1. 1, 3 times 5 is 15. Check. So whatever number I plug in for n, I'm going to get that term in the sequence. So if I plug a 21 in there for n, I'm going to get the 21st term in the sequence. So when you plug a 21 in, what do you get? You get 5 times 3 to the 20th. Well, 3 to the 20th is pretty damn big. I'm very curious what your calculator said. What did your calculator say?
3 to the 20th. 3, 4, 8, 6, 7, 8. 4, 4, 0.
So 3.486?
No. It's a big number.
Oh, okay. So, yeah, but I thought maybe it was times 10 to the, I didn't know we're going to. So 3, 4.
4, 8, 6, 7. 8, 4, 4401.
Yummy. All right. That's how big the blob will be in 3 days. 21 days.
I got the answer.
You got it?
I had to go to my phone to do it.
Oh, well, it costs enough money. They should be able to do it. They just can't make phone calls.
17,433,922,005.
Is that for this?
Yeah, just for that. Or times 5.
Multiply by 5.
Oh, so you didn't multiply by 5 yet?
No,
Oh, okay.
20.
There you go. So now if you multiply by 5, I figure this should have been
1.74 something times 10 to the root of.
Can you be a little more specific?
No.
10 to the 10th? All right. Because this is 3, 6, 9. So times 5 will take it up to 10. That makes sense. Cool. I like it. So part of that was just to make sure you guys could actually interpret what your calculator says. Because sometimes we just don't run into scientific notation numbers on a calculator very often. Somebody will do this and they'll tell me the answer is 1.74. Okay, wait. 5 times 23 is 1.74. You know, so just be careful when your calculator is trying to say really big. Sometimes it'll give it to you scientific notation. On a scientific calculator, very often it just has at the end a little 10 up here. On the graphing calculator's thing, it's got the E. E something, yeah. I like it. Yes, sir.
So why do you choose 21?
Just because. I totally just felt like it. So they're going to have to ask you specific questions. You know, and again, this is not too far off from growth models of, like I said, I wasn't really joking entirely, of virus, how viruses spread. This could possibly model something like that, taking into account all the other variables. This could model the spread of, and it would be this many acres today and this many acres tomorrow, or 21 days later, and you're like, holy shit, I thought that movie was 28 days later. Take a week off and we're still pretty bad off. Sorry. All right. So that obviously can get big very quickly because it's based on multiplication. Now here's the weird part. If I wanted to add up so many terms of this, and I don't think the book actually shows you this, they just give you the answer. So I'm going to try to show you why this works. Let's see. So I want to figure out what the sum of the first n terms is. So let's write down what it would be. Just go with me on this. In fact, you don't even have to write this down if you don't want to. You just watch and go, what the hell's going on? So this would be A1 plus, now let me see if you guys are with me on this. The basic idea of a geometric sequence, how do you get to the next term? Whatever term you start at, how do you get to the next term? You multiply by r. The first term is A1, there's no question. That's the definition of freaking A1, is it's the first term, whatever it is. Is that cool? So what is the next term going to be? What'd you just say? How do I get to the next term? I multiply wherever I am by r. So the next term is going to be A1r. With me? Because if I wanted the second term here, I would just put a 2 there. 2 minus 1 is 1. R to the first is r. A1 times r. That's the second term. In not number speak, just pure letter speak. Right? So what's the next term after that? What do you do to that term when you get the next term? You can do it. What do I keep doing? I'm always doing what? Multiply by r. So what's A1r times r?
A1r squared.
A1r squared. Beautiful. Just a little bit of algebra sneaks into this class, I know. So A1r squared. Up to what for Sn? Be careful now. Careful.
A1r.
I love it. I like it. Remember that because we don't start at A0, it's always a little screwed up. To get to the nth one, it's n minus 1, because I got to do one less step. All right, maybe.
So to shorten that, it's just
S of n is a1 times r to the n minus 1 power?
No, definitely not, because they're these like terms. I can't combine them. This is it. This is what it is.
All the way
Now, if these were numbers, I could figure out what the numbers were and then combine them. Right? I mean, if this is the sequence, I could figure out this is 5, 15, 45, and if I go with the 21, I'm going to get this sum. Right? But this is, I need to develop a formula that works no matter what the sequence is. So if I have a geometric sequence, do you all agree with me that this here would represent the first n terms? Let me sneak out of that, whatever that was. Are you guys with me on this? The A1 is the first term. How do you get to the next term if it's geometric? Multiply by whatever the hell R is. Then just keep doing that. Just keep multiplying by R. Yes, sir?
Does that mean you couldn't write it as n equals a1 times r to the n minus 1? Just that?
No, because what would happen to these? Where would they go? Are you telling me that this plus this plus this plus this is just equal to only that? That can't be true, right? I kind of know what you guys are trying to do, but this is the sum, not just a list with commas. This is the sum of all of these terms. They all have to be there. Now, let me see. Now, again, this is a derivation of a formula. I just told you, you didn't even have to write this in your notes. I'm not going to make you do this. All right, some of you guys have already turned off, and you're just kind of giving me the nice, you look in my direction. I appreciate that. Now watch, this is a cool little trick. If I multiply this by r, what do I get? What's r times a1? A1R, look, somebody's like in the back going, pineapple? I don't know what the hell. I always love that. I love that. I'm like, when I ask my Math 90, what's x times y? They're like, z? I don't know what the hell it is. xy. So if I multiply both sides by r, I get r times this. And why am I putting it there? This is kind of like terms then, right? What's r times a1r squared? Or a1r, sorry. a1r squared. All the way, and then what's r times a1r to the n minus 1? Uh-oh. Oh, shit.
a1 r to n minus 2.
Nope. What's r times r squared? Because 1 plus 2 is 3. So what's r times r to the n minus 1? What's 1 plus n minus 1? N. What do you do with powers? When you multiply like bases, you add them. So 1r times n minus 1r's is nr's. Why the hell did I just do that shit? Because I'm weird. What is, now watch, this is kind of cool. Let me make sure I go the right way with this. Yes, okay. What's this minus this? Sn minus r Sn, right? Ooh. What? Now watch. What's this? So I just subtracted this from by this, right? So I'm going to do the same thing to this side. A1 minus 0 is A1. This cancels. This cancels. All this shit in the middle. And even this cancels. And what am I? I'm left with just that. Again, this is a derivation of a formula. If you're not entirely with me, I can live with that. And so can you. But this is kind of a nifty trick that we use in a lot of different places. Yes, sir?
So we're not going to have to know this?
You're going to have to write down the formula that we end up at.
Because you totally lost me.
I understand.
Sure.
I'll show you an example that you might have seen before related to how to write decimals as fractions. Repeating decimals. We'll see if that helps out a little bit. Go ahead. So what I just did was to try to take this. Now this sucks. This sucks for a formula because it just says find what the next one is and add it. Find what the next one is and add it. And the whole point of this is I don't want to do that shit. I want to be able to get the sum very quickly. I don't want to have to find what's the sum of the first 1,000. You're going to need 1,000 numbers. No. Right? You're going to have a bad time. So let's not do that. Let's do this. Now watch. Even if now the reason I did this is because I noticed that so many of these would cancel if I did this kind of thing subtracted. It just would make the problem a lot more consolidated. So it's a trick that math people learned a long time ago. They said, let's try this. It worked. Will it work somewhere else? Yeah. And we just went crazy. We just did it all over the damn place. So this is now an accepted kind of thing to try, when you try to make a formula look a little better. Now watch this. This is a little bit of algebra. I could take an Sn out. I get 1 minus r. Right, if I factor an Sn out. I love you. You guys are all like, I was told there wouldn't be any algebra, but there has to be a little bit. And I can take an A1 out of here, right? And then to get Sn, I just got to divide by 1 minus r. So now, if you tuned me out, come back in. Come back in now. That is the formula for the sum of the first n terms. I warned you that I was not going to be pretty because I'm adding a bunch of multiplications. There's no reason to believe it's going to be pretty. Now real quick, before we do an example, I want to show you something, and I'm curious as to how many of you guys have ever seen this before. You guys all know what 0.3333 forever is as a fraction, right? Do you? Normally people do. What is that as a fraction? 1/3. Normally people know 0.333 forever is 1/3. Alright, so now watch this, watch this. You can actually get the answer to what I'm about to do, but I'm going to show you how to do it for anything. So let me start. What 0.11 forever? So say I'm not sure what the fraction is. So in algebra, what do I call something when I don't know what it is? X. And the reason we do that is so I can do shit with it. So here, if I call this X, now this is definitely extra right now, but I want to see why this kind of thing makes a little bit of sense. Why does 0.11 forever suck? Part of what I just said. Why does it suck as a number? Poor little dude, because it never freaking ends. It goes forever. Holy shit, how can I work with that? So if I had 0.11, what is that as a fraction? What is 0.11 as a fraction? Beautiful, because it's in the hundredths place, right? Good old place value shit from chapter 4, yeah! So our place values are based on 10, so at the decimals, 1/10, 100th, and so forth. So for 8, base 8, it'd be 1/8, 1/64th. Okay, we won't go there. So now watch this, it's kind of cool. So if the thing that sucks about the number is that it has a forever amount of ones, it never stops with ones. Watch, if I multiply this by 10, what happens to a decimal when I multiply by 10? The decimal moves over, so it gets bigger, of course, right? So this would become 1.11 forever. And I'm going to do something like I just did here. And you can see why. This didn't even have as many problems as this did, right? But it still has some problems. And now you see why. Now, 10x minus x is 9x. 1.1 forever minus 0.1 forever. What happens to the 0.1s forever? What happens to these? Yeah, they can't. All of them cancel forever. They cancel and I get 1. So x was the original problem. So when I solve for x, I get 1/9. If you divide 1 divided by 9 in your calculator, it'll tell you 0.11111 as far as it can. And it goes, that's as much as I could do, man. Just keeps going. So something interesting is, so that's 0.1 forever. What's 3/9? Multiply by 3, right? 3/9 would be 0.3.